Assalamualaikum warahmatullahi wabarakatuh. We are from Group 6. Today we will present about the Aeroheart magnetic levitation LVAD. As we know, LVAD used to help patient with heart failure. So today we will present about how magnetic levitation can improve the pump performance, reduce damage to blood, and increase patient safety. Okay, next we will go to the advantage of the magnetic levitation pump. The Aeroheart device uses a centrifugal pump with a backward curve impeller. It will produce smooth blood flow. Next, the system also uses full magnetic levitation, where the rotor float without touching any mechanical part. So, there is no contact between the rotor and the other moving part. It will reduce the friction and the wear, and it also improve the durability and lower the power consumption. Next, the wider blood flow path also reduce the shear stress on blood cell. This will help to reduce complication such as blood clotting and blood cell damage. Okay, next we will compare two LVAD design, which is for the adult and for the pediatric patient. For the adult device, we prefer use the centrifugal flow pump with full magnetic levitation. This design provide lower shear stress, better hemocompatibility, and excellent rotor stability. However, its larger size make it less suitable for the pediatric patient. For the pediatric device, the main priority is miniaturization. So the pump can fit into the child thoracic cavity. Therefore, axial flow pump with a hybrid magnetic levitation is selected because it's more compact and easier to miniaturize. However, this approach introduces high shear stress and increase the risk of the hemolysis and thrombosis. But we are, as an engineer, we will reduce the risk of the hemolysis and the thrombosis risk to make this device more safe for the patient.
I will explain failure modes and effect analysis, which is FMEA. Uh, FMEA is a systematic method that we use to identify the potential failure, uh, to evaluate the failure, and then how to overcome the failure to ensure the patient safety. In this project, we already identify three critical failure modes, which is total power loss, Hall sensor failure, and also control algorithm failure. Total power loss is it will happen when electrical power to the system is completely lost. When this thing happen, the magnetic field collapse, and then the rotor is not longer levitated, and the pump may stop immediately. So it will the primary effect is the immediate loss of the blood flow, which may lead to cardiogenic cardiogenic shock and also organ failure. So how to overcome uh, this uh, this failure? First is we we apa we to overcome this failure, we implemented dua redundant batteries. Why we choose this we do the redundant batteries when it may provide it will act as a backup if the primary battery failed. And then the second is super capacitor. We choose super capacitor because it can deliver energy uh, almost instantly and allow control rotor spin instead of absurd stop. And then the next is passive touchdown bearings. So we choose passive touchdown bearing to support the rotor if the levitation is lost and preventing the direct contact damage. So the second failure mode is hall sensor failure. So this hall sensor is used to detect the rotor position within the magnetic and within the magnetic levitation system. So if sensor fail, the control may receive incorrect position. The incorrect position information cause will lead to rotor instability. So this may increase shear stress and lead to hemolysis and also thrombosis. So we to overcome this failure, we implemented triple Hall sensor, triple Hall redundancy. So if one fails, the other two can still provide valid measurements. So it still can work properly. The second is majority voting algorithm. So majority voting algorithm was selected because it allows the control to use the value agreed upon by at least two sensors. And lastly, we choose sensor back EMF. Uh, this sensorless back EMF estimation selected as an additional backup because it can estimate rotor position from motor voltage even when sensor reading become unreliable. So the last failure modes is control algorithm failure. So the control system operates at 10 kilohertz update per second. This one is to maintain the rotor stability. So if the algorithm crash, so the pump speed may move outside the safe operating range. So this can be lead in a ventricular suction or regurgitant flow or loss levitation. So to address this we implemented dedicated FPGA hardware to watch uh, uh, FP FPGA was selected because it provide deterministic real-time processing and can reliably execute the 10 kHz control loop. And the second is watchdog timer. So watchdog timer was selected to detect the control unresponsiveness and automatically reset the system. And the lastly is the open loop default modes was selected to keep pump operating at a safe speed even the algorithm fails. So overall, the MEA identified three major risks involving power, sensing, and control. So each failure can lead to severe complications such as cardiogenic shock, hemolysis, thrombosis, and ventricular suction. Therefore, we selected mitigation strategies that provide redundancy, fault detection, and fail-safe operation to ensure continuous and safe pump performance. That's all from me. Thank you.
Good day and Assalamualaikum everyone. To understand how we control an artificial heart, we must first look at the hemodynamic challenge. An artificial pump operates within a very narrow, safe window. If the pump speed is too slow, we face regurgitant flow, where blood actually flows backward from the aorta into the ventricle. However, if the pump is too fast, we risk ventricular suction, where the pump outspaces the heart's filling rate, causing the heart tissue to collapse. To navigate this, we cannot rely on manual setting. We need adaptive closed-loop control. Next slide. To manage this complexity, our system use a three-tier physiological framework. The first layer is the perception layer. This is our data acquisition. We use 3-axis accelerometers to detect if a patient is resting or exercising, and differential pressure sensor to monitor the load of the heart. And then for the second layer is the cognition layer. This is the brain of the device. It uses supervisor logic to calculate adaptive set points, ensuring we balance the needs for blood flow against the risk of suction. And then for the third layer is the execution layer. Finally, the PID controller translates this decision into action, regulating the Maglev pump speed via PWM signals. And then for the next slide is a key feature of the system is biomimicry, specifically mimicking the Frank-Starling mechanism. In a healthy heart, increased blood return stretches the heart walls, automatically increases the stroke volume. Our algorithm replicates this. When the accelerometer detects a demand trigger like walking, the sensor detects a spike in preload. The PID algorithm when instantly increases the rotor RPM, elevating the cardiac output to match the patient's new metabolic reality. And then for the next slide is control isn't about the speed, but it's also about multi-objective optimization. We are constantly balancing 3 points here. So for the first one is maximizing perfusion, keeping the cardiac output between 3 until 6 liters per minute, and then regulating pressure, keeping the arterial pressure within the safe limit, and then preventing suction, ensuring arterial pressure stays strictly above 0. And then safety is paramount. If the sensor fails, the system triggers an ultimate fail-safe, reverting to an open loop default mode. A constant speed sufficient to sustain life, while physically guaranteed to avoid suction. And then for the next slide is, in conclusion, this unified control architecture integrate hierarchical logic with real-time plan telemetry. By utilizing this governing equation, we transform a static mechanical pump into a biomimetic artificial organ. This ensures that the device doesn't just pump blood but respond dynamically to the human body. Thank you for your time.
The Aeroheart is a Class 3 medical device necessitating a FDA pre-market approval (PMA) for life-sustaining implant. The development process utilized the V model verification, a focus on whether the system was built correctly according to technical design specification. Validation is a focus on whether the right system was built, ensuring clinical efficiency and patient safety. Engineering reliability is verified through rigorous standard, hydraulic and hardware. ISO 1470085 attested via more circulatory loops (MCL), verify continuous operation at 6 liters per minute against 100 mmHg. Durability: the driveline is tested to withstand 100,000 flex cycle. Code and computational ASME VNV40 embedded control software is stress tested at 10,000 Hz for latency and race condition. Hemocompatibility ASTM F1830 desktop both blood testing proved the normalized index of hemolysis NIH remain below 0.01 gram 100 per liter. The system is validated within biological and human environment. In vivo study, 30 to 19 large animal models are used to confirm the absence of infection and sustain organ perfusion. Biocompatibility, ISO 10663 and materials such as titanium alloy and permanent magnet are validated to ensure zero systemic toxicity or chronic inflammation. Human factor IEC 62366 simulate a use of province that patient can interpret alarm and sweat battery within a 3-minute emergency window. The path to ultimate approval involves several stages. Phase 1 is IDE submission. The FDA grant an investigational device exemption based on previous verification and validation data. Phase 2, early feasibility EFS, safety and surgical technique are validated in a small cohort of 10 until 50 patients. Phase 3 is pivotal trial, large trial, compare the Aeroheart against existing marketing predicate such as HeartMate 3. Endpoint FDA PMA approval is based on the patient's survival for 6 to 12 months without disable stroke or pump replacement. The Aeroheart system is an integration of 3 core pillars: hardware architecture, centrifugal flow with Maglev technology and low power consumption, biomimetic intelligence, a 10,000 Hz control loop mimicking the Frank Starling mechanism, regulatory part, a comprehensive V model verification and validation, a final takeaway, a flawless hardware requirement dermatitis control, and rigorous regulatory proof to function as life-sustained artificial organ. Thank you.